Okay, now let's look at how we can go from conditional probability to the Bayesian theorem. Now, there's a lot of mathematical expression as you can see here, but we'll take it one step at a time. So we're going to go from conditional probability to the Bayesian theorem. Now, what you need to know is that there are different ways you can express the Bayesian theorem. Let's see how we can derive the Bayesian theorem from conditional probability. So here we are told that the probability of A given B is equal to this expression, the probability of B and A over the probability of B. Had we swapped B and A, or rather, had we swapped A and B with B and A, we would have gotten a similar expression on the right. Instead, in the denominator, we would have had A instead of B. The numerators obviously are equivalent. When you perform the intersection of two sets, it is commutative, so the order doesn't matter. But let's talk about equation 1. If we take probability of B and multiply in both sides, so probability of B here and here, probability of B will be cancelled out from the denominator and it will appear here on the left. So we would get this equation. Okay, as you can see, probability of B has moved from the denominator over here to the left. Had we done the same thing for equation 2, where we cancelled or where we multiplied the probability of A on both sides of the equation, we would have gotten this. So probability of A has moved from the denominator here to the left. Now please pay close attention to these two equations, equations 3 and 4. It might be a good idea for you to pause here and then go back to the start of the video and make sure you've seen what we've done so far. All we've done is multiply both sides of the equation with the marginal probability to move from the right to the left, to move it from the denominator to the left. But anyway, we said that these two can be moved around. Intersection is a commutative operation. So whether we say probability of B and A or the probability of A and B, it's the same thing. In other words, equation 3 is equivalent to equation 4. And if the equations are, equal to one another, if the equations are equal to one another, then the terms on each side of the equal signs are also equivalent. So if probability of B and A is equal to that, and we said that intersection is commutative, which means this is also equal to that, and we can see that probability of A and B is equal to that, that means the probability of B and A is equal to that. And if I remove these two expressions here in the middle, we will get this. They are equivalent. If we were to divide both sides of the equation with the probability of B, then we would have equation 5b. Right? we move probability of B to the other side. It's now in the denominator. But up here in equation 5, we said that the probability of B given A times probability of B is equivalent to the probability of A given B times the probability of B. So another way to write this is that these two are equivalent. Okay? Again, it's a good idea for you to maybe write this down and work your way up to this point before you continue. All right, let's move down. Let's move on. The probability of B. We can replace this marginal probability with the sum of joint probabilities. If you remember from the example where we had the table of frequencies and the marginals, we saw that the probability of B was the sum of its intersection with A and with the intersection of the complement of A. To refresh your memory, let me pull up that example. This example. Probability of B and A will give you 5. Probability of B and not A, or the complement of A, also 5. Add these up and you will get the sum, which is equal to the marginal probability. Okay, so again, the probability of B is equal to the sum of these joint probabilities. This is true no matter what the events are. Now, probability of B and A. Bring your attention here. We said that this is equivalent to up here. We said that this is equivalent to this expression. Yes? We said that the probability of B and A is equal to the probability of B and A is equal to this expression. But we also said that this expression is equal to that expression. And so we can substitute the probability of B and A with this expression by equivalence. By equivalence, we can replace this with that. Similarly, we can replace this with a similar looking expression, except here instead of A we have the complement of A. And this is what we are going to use. We're going to use this form of the Bayesian theorem at the next example. Now this is the probability version. There is also a likelihood version of the Bayesian theorem, but that's for the next section. But it's important for you to see that the Bayesian theorem looks simple, but it requires this axiomatic thinking to understand how we could go from conditional probability to different algebraic arrangements. And even the Bayesian theorem can take on different forms, which is why if we were to look up Bayesian theorem online, you would see that this formula is expressed in different ways. And that is because of equivalence, we can do so. It will be a good idea for you to try to do this yourself as well as an exercise. Go from conditional probability to the Bayesian theorem.